Good morning, everybody, and welcome back to Abstract Algebra. Yes, Peter, it's always a pleasure. 4, 5, 6, 7, 8, 9, 10. Cool, we're over half. Plan for today, we are going to finish off our discussion of Chapter 6 by talking about isomorphisms, topic that we've kind of been approaching with our discussion of homomorphism so far, but I'm going to add a little twist to that today. Upcoming office hours, got my usual hours on Monday. Hours for class and from 2 to 3. And as a reminder, exam 1 is due next Wednesday. So just like the homeworks, the exam won't be due until the end of the day, so you'll have until 11:59 p.m. on Wednesday. And so yes, you will be able to meet with me during my Wednesday office hours and ask questions and such. Any questions or comments before we get started today? So, the heat was not working in this building yesterday, so that inspired this joke. If you're in a cold, where should you stand in a cold room if you want to warm up? Yes, Peter?
Corner, 90 degrees.
You should stand in the corner because it's always 90 degrees there. Okay, so plan for today is we're going to finish off this packet, which means we'll be ready for another one come Monday. So, the last few classes, we've been talking about these functions called homomorphisms, which are functions from one group to another group, satisfying if you take satisfying that if you multiply two elements in the first group together and then apply your function phi to get something in G2, we get the same thing as if we took phi of A, group operation from second group, phi of B. So in other words, combining them and then applying the function phi comes out to the same thing as applying the function phi and then doing the group operation. And so what I want to do today is I'm going to finally answer our question from a couple classes ago, which is, you all thought that these two groups are mathematically the same. Today we're going to go through and actually prove it by coming up with a definition of what it means for two groups to be mathematically the same, even if they look a little bit different. And that is going to take us to our definition of isomorphism. So I'm going to be on the second to last page of the packet, which says a group isomorphism from at the top. And to define a group isomorphism I've been specifying group homomorphism and group isomorphism in the definitions because there are other types of homomorphisms and isomorphisms, which we'll see towards the end of the semester. But a group isomorphism from G1 to G2 is going to be a function, phi from G1 to G2, such that, first of all, we want phi to be a homomorphism. Homomorphism. I always find out that if I try and write out the word homomorphism, I get lost about halfway through, and it's like, do I need another mode or not? We also need that phi is 1 to 1, and then phi is onto. Well, you may remember we said that a function is 1 to 1 if no two inputs map to the same output. So in other words, phi of A equals phi of B will imply that A has to be equal to B. It's impossible for two different things to map to the same thing under phi. And we also claim that, the third condition we need is that phi is onto. In other words, given any element B in our second group, there exists some element A in our first group with phi of A equal to. And we say that if we have a group homomorphism that has these additional properties of being 1 to 1 and onto, then we call it a group isomorphism. Before I do the example, And if we have two groups, and if there exists an isomorphism between the two groups, we call the two groups isomorphic to each other. If an isomorphism P from G1 to G2 exists, we say G1 and G2 are isomorphic, which the shorthand notation for that is going to be this. G1 isomorphic to G2. So the isomorphism symbol is just like an equal sign with a little squiggly above it, a tilde, if you will. And this is going to be our kind of mathematic definition of what it means for two groups to be mathematically the same. The formal way of saying that is that they are isomorphic, meaning there's an isomorphism from the first group to the second group. So let's think about that for a second. So if one of these functions exists, we say that two groups behave mathematically the same. The inherent reason as to why we say that is, first of all, these two conditions, phi is 1 to 1 and phi is onto, what that basically tells us is that, first of all, phi is a map that touches every element in both groups. So phi being onto is necessary for everything in G2 to be connected to something in G1. And in fact, these two conditions combined tell us every element in G2 gets mapped to exactly once by an element in G1. Condition 3, phi being onto, tells us that everything in G2 gets mapped to at least once by elements in G1. Given any element in G2, there exists at least one element in G1 that maps to it. And 1 to 1 is going to tell us that we can't have multiple things mapping to anything in G2 because that would violate the 1 to 1 condition. So combining these two conditions together is going to tell us that every element in G2 gets mapped to exactly once. And so you get this unique 1 to 1 correspondence between elements in G1 and elements in G2. And the fact that phi is also a homomorphism is going to tell us that G1 and G2 have the same basic group structure to them. Doing a group operation in G1 is essentially the same as doing the group operation in G2. Even if they look a little bit different, they're inherently going to be the same. So let's look at a couple examples, see if we can kind of make sense of what I'm trying to say. So I want to define a function. I'm going to define it phi from the integers to 3z. And I claim that the function phi of x is equal to 3x is going to be an example of one of these group isomorphisms. So let's see if we can prove this. So in order to prove that phi is a group isomorphism, we need to check three things. We need to check that phi is a group homomorphism, that phi is a 1 to 1 function, and that phi is onto. Peter, which one would you like to check first?
I'm sorry, can you repeat the question?
If we want to show that phi is a group isomorphism, we need to check three separate properties.
Mm-hmm.
Which one would you like to check first? Doesn't really matter.
First one.
First one, start at the beginning. All right, so the first thing we'll check is, let's check to see if phi is a group homomorphism. So to do that, we need to be able to take two elements in the first group, in the group of integers, and show that if we do phi and then the group operation, you get the same thing as if we did the group operation and then phi. So given any elements, I'll call them A and B and the integers, our group operation in the group of integers is just going to be addition. So if we take phi of A plus B, by definition, that's going to be 3 times the quantity A plus B, which in turn is just going to be 3A plus 3B, which is equal to phi of A plus phi of B. So we have a group homomorphism, where if we add in the integers and then apply them at phi, we're going to get the same thing as if we if we took phi of A and phi of B separately and then added them in the group 3z. Sydney, let's check 1-to-1 or onto next? Check 1-to-1. Just going straight down the list. Okay, so now we need to check if phi of A is equal to phi of B, does that mean A equals B? So if phi of A is equal to phi of B, well, by definition, that's going to mean 3A has to be equal to 3B. And if 3 times the integer A has to be equal to 3 times the integer B, Dolly, is that going to tell us that A has to equal B? I think it does. Because you can just divide both sides by 3. Any questions or comments so far? Last thing we need to check, is this function phi onto? Well, given any element, let's say A in our second group, so our second group is 3z, what does it mean for A to be in 3z? If A is in 3z, how can we write that out using an equation? Right?
A equals 3b if b is an integer.
Yeah, A has to be equal to 3 times 3b for some integer b. A must equal 3b for some b, an element in the integers. Hence, if we write this all out, we could say that A is 3b is going to have to be phi of that b. So in other words, given this arbitrary element A in our second group, the group of multiples of 3, we're going to say that A has to be equal to phi of b, where b is the thing that you would multiply by 3 to get A. Yes?
Would be the case that if it's onto, that the image of phi is just the group?
Correct. Yeah, that's a good question. Like, if we have an onto function, then the image of phi is just going to be the entire second group D2. Or in other words, you could say that if a function is onto, then the range and the codomain of that function are going to be the same set. So phi is a group homomorphism. It's 1-to-1, and it's onto. So this is all going to tell us that phi is a group isomorphism. Hence, the integers are isomorphic to the set of all multiples of 3. So, if any of you have studied classics and learned a little bit of Greek or Latin, anybody know what iso and morph mean?
Well, morph is change, right?
Morph sort of means change, or like the same, like, or it refers to something about like the change in structure of something.
I think iso means the same.
Yeah. So the word isomorphism really just means two things that have the same form. We kind of break it apart into like it's, I don't know if that's Greek or Latin. I am not a classic person, I cannot tell you. But basically, the word isomorphism really just means two things that have the same form to it. If you have two groups, and if there is an isomorphism from one group to the other, we say those two groups are isomorphic, meaning they have the same form. They're mathematically the same, even if they look a little bit different. It's kind of interesting. The group of all integers is isomorphic to one of its subgroups. Basically saying those two groups may look a little bit different, but they behave in exactly the same way. To a mathematician's viewpoint, they might as well be the same group. In this example, we could have replaced 3 with any non-zero integer n, and the same argument would have worked. Z is also isomorphic to 2z, 4z, 5z, 6z, etc. Any questions or comments? Let's go back to our example from the front page. So these were the two groups on the front page that you all decided were mathematically the same. They appeared to have like a bunch of similar properties to each other. So this one is just this first table is just the Cayley table for z mod 3z. The second one is one I made up, where I replaced 0, 1, 2, and 3 with letters instead of having numbers. I claim you can find an isomorphism from the first group to the second group. So I'm going to call this group G1, and this group I'm going to call G2. I claim G1 is isomorphic to G2. And to prove that, we just need to construct a function from the first group to the second group that is going to be an example of one of these isomorphisms. So let's do that. Gabe, what's your favorite name for a function? F. Okay. Let's construct an isomorphism from G1 to G2, which we'll call F. Since our second group in particular isn't like, we can't do this with just a nice formula. In order to define our function F that'll do this, we basically just need to say, what does f of 0 equal? What does f of 1 equal? What does f of 2 equal? What does f of 3 equal? So we'd like to come up with a function that is a isomorphism from the first group to the second group. Anybody have a candidate for where they would like to map the number 0? Where 0, keep in mind, is the identity element of the first group. Why?
To A,
Why do you say A?
because it's the identity element of the second group.
Yeah. It's going to turn out to be the case when you have an isomorphism, fun fact, the identity of the element of the first group has to map to the identity element of the second group. We saw that, by the way, when we were looking at homomorphisms and said a homomorphism has to map identity to identity. And since isomorphisms are all homomorphisms by definition, the isomorphism will have to map the identity element of the first group to the identity element of the second group. So we can map f of 0 to A, f of 1. Nick, have anywhere you'd like to map f of 1?
Just the B.
Okay, f of 1 you want to map to B. Becca, how about f of 2?
C.
And Steph, f of 3?
D.
So our claim is this is going to be an isomorphism. Well, I think if we look at it, it's certainly going to be 1-to-1 because no two elements map to the same thing. 0, 1, 2, 3 all map to the unique elements. It's also going to be onto because every element in G2 gets mapped to by something. A gets mapped to by 0, B gets mapped to by 1, C gets mapped to by 2, D gets mapped to by 3. And F is going to be a homomorphism because I don't want to prove F is a homomorphism. That involves technically checking like 13, I think, different equations to make sure they all hold. You need f of 0 plus 0 equals f of 0 plus f of 0. F of 0 plus 1 equals f of 0 plus f of 1. F of 0 plus 2 equals f of 0 plus f of 2. Or f times f of 2. F of 0 plus 3 is f of 0 times f of 3. F of 1 times f of 1 is f of 1 plus 1. F of 1 times f of 2 is f of 1 plus f of 2. F of 1 times f of 2 is f of 1 plus 2, etc. We have to check like all of these different equations to make sure they're true in order for it to be a homomorphism. If you want to check, be my guest. I'll just tell you it works out. But the fact that you all thought these two groups look the same is actually going to be as a result of them being isomorphic to each other. Would y'all like to see a twist? Let's see. There's another isomorphism for you. Just because you have two groups and you can find one isomorphism between them doesn't mean you can't also potentially have other isomorphisms. Okay.
Will any isomorphism have to have like f of 0 equals a though?
It would. And that comes from the fact that that's a property of homomorphisms we proved last class, the property that said a homomorphism, if you have a group homomorphism, then the identity of the first group has to map to the identity of the second group. Also could have had a third, there's also a third one that maps 1 to D, 2 to B, and 3 to C, I think. That'll also be an isomorphism. But no matter what isomorphism you would take, 0 has to map to A. If 0 doesn't map to A, then the homomorphism property isn't going to work out. Question. And so, since such an isomorphism exists, we say these two groups are isomorphic to each other, meaning they are mathematically the same. Questions or comments?
It seems like all these isomorphisms are like a same cyclic group. You're just rearranging them.
Yeah.
Same cycle.
Exactly. We're just basically rearranging the same group, kind of like twisting it in a different way, but we're still getting something that has the same basic, properly behaving underlying group structure to it. So G2 we can say is going to be isomorphic to this Z mod 3Z group that we started with. Here's a fill-in-the-blank question for you. So basically, well, actually, before I ask the fill-in-the-blank question, I'm going to preface it by saying, you can show that while there may be something like an infinite number of groups of order 4, you could always just rearrange the letters and symbols to be whatever letters and symbols they want. You can also classify groups in what are called isomorphism classes, where two groups are in the same isomorphism class if they're isomorphic to each other. And anyone want to make a guess how many different unique groups of order 4 there are that are not in the same isomorphism class? Meaning, if you have groups of order 4, how many different possible groups of order 4 can you have that are not isomorphic to each other? Right?
I guess 10.
I guess it's 10. Here?
I guess 1.
It's not 1 because we found 2 on the front page.
But you said the ones that are isomorphic to one
True. We found this third group that isn't isomorphic to these two, though, on the front page of the packet.
another. Well, fine.
Be that way, Dr. Bursell. Turns out, answer's 2.
Oh, I was closer. That's Price is Right rules, right?
Yes, good job. You win. Don't shake hands. There's COVID. Gosh. Okay. Turns out there's only 2 groups of order 4. There is a single group of order 1, a single group of order 2, a single group of order 3, a single group of order 5, a bunch of groups of order 6, a single group of order 7, 3 groups of order 8, etc. Here's the fill in the blank question. Not 2,000. Turns out, if you take all the groups of order less than 2,000, 2,000 or less, turns out 99+% of them all have the same order. Anyone would like to guess what the order that is? Peter?
Is it order 1?
It's not order 1 because there's only a single group of order 1.
But you said you can have any different symbol.
Distinct non-isomorphic groups, I should say.
I'm straight up.
Is it 27?
It is not 27, though that would make me very happy. 27, actually, there's only a few groups of order 27. There's not very many.
2.
Not 2. It's only one group of order 2.
Okay.
Right?
Is it 2,000?
It's not 2,000. One more guess.
10, so we haven't used that one in a few guesses.
Nope. 1,024.
That was my next guess.
I'll give you a hint. The number of groups, of non-isomorphic groups of a certain order you can have is going to be tied heavily to how many prime factors does that number have. And 1024, which by the way is 2 to the 2, 4, 8, 16, 32, 64, 128, 2, 2, 6, 5, 12, 10, 24, is 2 to the 10th. The fact that we have 10 distinct prime powers, well, okay, not distinct, 10 prime factors here, 2 coming a lot. The more prime factors you have, the more groups of that order, non-isomorphic groups of that order you can have. And 1024 has a lot of prime factors of 2 in it. And so it turns out if you add a single prime factor to your group, then suddenly you get a lot more groups of that order. If I had changed this, by the way, to 3,000, then I could have said 99%+ of groups of order less than 3,000 all have order 2,048 by similar reasoning. I think. No, I'm not going to prove this. That would take the entire rest of the semester to actually prove this fact. But it's kind of cool that this felt really cool to me that there's so many groups of order 1024. It's far more than the groups of every other order less than 2,000 combined.
So adding just one more prime factor increases it that drastically, where 512 is less than 1% of the groups, but 1,024 is over 99%.
Correct. I think if we were to ask the same question, I'm not sure if this is true for 512. I'm guessing that a very, very large percentage of the groups of order less than 600 have order 512. Make similar sorts of statements like that. This is not something I expect you to know or to memorize or anything like that. It's just kind of cool to me. It's there's so many groups of that order just because 1024 has a lot of prime factors to it. Whereas 27 only has 3 prime factors, it's 3 cubed, and so it has a relatively small number of groups of that order, as opposed to say 20, something like 28, which has, what's 28, 2 squared, 2 squared times 7. Oh, it actually has more than 20, never mind. I like 27, but that's all I'm going to say about it for now. Any other questions about these isomorphisms? Check out the back page of the packet. So, two groups, if there's an isomorphism between two groups, here are some of the properties that isomorphism has to have, which is basically telling us what does it mean for two groups to be mathematically the same. They have to have the same order, meaning there's the same number of elements in each group. One is abelian if and only if the other is abelian. One is cyclic if and only if the other one is cyclic. If phi is our isomorphism, then any generator of G1 has to map to a generator of G2. The identity has to map to the identity, which we've already seen. G and H commute if and only if phi of G and phi of H commute. The order of any element in the first group has to be equal to the order of whatever that element maps to in the second group. G1 and G2 have to have the same number of elements of every order. So G1 had, so for instance, we said this group has one element of order 1, no elements of order 2, and 3 elements of order 4. Well, any other group that this thing is isomorphic to is also going to have just one element of order 1, no elements of order 2, 3 elements of order 4. Phi inverse is an isomorphism. If phi is an isomorphism, then the functional inverse, which should exist since phi is 1-to-1 and onto, we know there is an inverse map. Its inverse function also has to be an isomorphism. So isomorphisms work backwards. If G1 is isomorphic to G2, then G2 has to be isomorphic to G1. If H is a subgroup of G2, then the preimage of H, the set of all things mapping into H, has to be a subgroup of G1. And the center of G1 under our isomorphism has to map to the center of G2. Or you may remember the center of a group is just a set of all things that commute with, it's a set of elements that commute with everything in the group. All right, I will prove one of these. Anybody have one of these that they would like to see proved? And if you tell me to prove this, I'm just going to glare at you. Okay, Nick?
Number 5.
Number 5. Okay, we did that last class. I don't want to do that again. Number 5, by the way, is true for just plain old homomorphisms.
Number 2.
Yes, very close. Is that here?
Number 2.
Number 2, G1 is abelian if and only if G2 is abelian. Sure, we can prove that. Basically saying if there's an isomorphism from G1 to G2, then one group is abelian if and only if the other group is abelian. So our claim is if phi from G1 to G2 is an isomorphism, then G1 is abelian if and only if G2 is abelian. All right, I didn't write down proofs for any of these in preparing for class. Let's see how horribly awry this goes. So let's go to the forward direction first. We'll show that if G1 is abelian, then G2 is abelian. So suppose G1 is abelian. And our goal is going to be to show G2 is an abelian group. So what do we need to do if we want to prove that G2 is abelian? What would we have to actually show? Yeah, when?
Show that 2 arbitrary elements in G2 are, have a property.
Will commute with each other?
Thank you.
Yeah, we need to show if A and B are 2 elements in G2, then A times B is equal to B times A. So let's do that. So let's let A and B be elements in G2. And our goal is going to be to show that AB is equal to BA. Because we can do that for arbitrary elements in G2, then G2 has to be an abelian group. Well, if A and B are in G2, part of phi being an isomorphism is that phi has to be onto. So we can say, since phi is onto, there exist, what do I want to call them? I'll call them C and D in G1, such that phi of C is equal to A, and phi of D is equal to B. I'm already regretting calling these A and B instead of X1 and X2. So that's just from phi being onto. Phi being onto from G1 to G2 just means that everything in G2 gets mapped to by at least one thing in G1. So since A and B are elements in G2, A has to get mapped to by something in G1, call it C, and B has to get mapped to from something in G1, call it D. Then if we wanted to take AB, by definition, that's just going to be phi of C times phi of D. Check this out. Since phi is a homomorphism, that's just going to be the same as phi of CD. Because phi of CD should multiplying C and D in G1 and then applying phi, if phi is a homomorphism, should give us the same thing as taking phi of C and phi of D separately, and then applying the group operation in G2.
Did we assume that G1 and G2 were using the same group operation?
We're not. So this is a little bit of sloppy notation. Technically, when I say phi of C times phi of D versus phi of CD, this multiplication in here does not have to be the same operation as this sort of multiplication. So really in here, we're using the group operation from G2. Here we're using the group operation from G1. I'm just being lazy and not writing out the different symbols for it. Because of laziness. And because typically in math, you don't write out the operations if it's kind of for an arbitrary group like this, unless there's a strong need to do so, which I don't think there is here. But since C and D are elements in G1, and since G1 is an abelian group, what do we know phi of CD has to be equal to? Yeah, Elaine?
Phi of DC.
Yeah. We know that these are going to be equal, and this is since G1 is abelian. C and D are elements in G1, so applying the group operation C star D in G1 should give us the same as D star C in G1. And then we can use the homomorphism property to break this back up into phi of D times phi of C, where again, here the multiplication is in G2, and my definition, that's just going to be BA. Thus, D2 is abelian. So in other words, if G1 is abelian, G2 has to be abelian. Do you all want to see the backwards direction of this, or should we prove a different property? I could swap in his hand. Different property. All right. It's a little bit harder, but pretty similar. Backwards direction is really easy if you assume the property that says phi inverse has to be an isomorphism, because then you can just use the forwards direction the second time. Okay, let's see. Here, I'll let you choose that first property to look at. Other Peter, would you like to choose a property from us since you wanted to prove something else, see something else?
Yeah, what about the number 7?
The order of G is equal to the order of phi of G. Okay. Do that one. For that one, I'm going to need a limit, which basically says if we take phi of g to the k in the first group, so g to the k just means g star, g star, g star, g over and over, then we're going to get the same, and if we take phi of g star, g star, g star, g star, g star, g, we're always going to get the same thing as if we were to take, in the second group, phi of g star, phi of g star, phi of g star, phi of g k times, which is basically just, and it turns out this is going to be something that's true not just for a group isomorphism, but for a group homomorphism as well. So here's the proof. We're going to let G be an element in G1, K be an integer. I'm going to let K be a positive integer, and then the proof for negative integers works very similarly. Well, then if phi is a homomorphism, that's going to tell us that phi of g to the k, which by definition is just going to be phi of g star, g star, g star, bunch of copies of g, k copies of g. Using the fact that phi is a homomorphism, we can split this up into phi of g star, g star, g star, g, k minus 1 copies. Times the phi of g. We can just basically say, hey, if we have k copies of g we're starring together, split that up into k minus 1 copies of g and 1 copy of g. And then the fact that phi is a group homomorphism tells us we can just split off a phi of g at the end. Which we can then use the homomorphism property of phi again to write this as phi of g star, g star, g, k minus 2 copies times a phi of g times a phi of g. Basically split off another phi of g from the end. Take the k minus 1 copy, split it into k minus 2 copies and 1 copy, and then apply the group homomorphism property. And then you basically just do this over and over until you've split off all of the phi of g's into separate elements. And then you'll eventually have k copies of this. And then that will just give us phi of g raised to the k power separately. So basically, we're just applying the group homomorphism property over and over and over again to basically say if we have k copies of g that we're multiplying together and then applying phi, that's just going to give us the same thing as taking phi of g times phi of g times phi of g, k copies of that. And then, so this only works if k is positive. If k is negative, just do the same thing with g inverse. Because basically, g to a negative power is just this, g to, like, say, the negative 5 is the same as doing g inverse to the positive 5th power. And then you just repeat this argument with k equals 5, but g inverse instead of g. I don't feel like writing that out. Okay, is everyone okay with my lemma? So again, this result doesn't require that we have a full isomorphism. It'll just work for a homomorphism as well. So now we can prove number 7. For all g in our second group. Okay, that's a typo. That's saying g1 for property number 7. For all elements in our first group, the order of g is equal to the order of phi of g. So here's basically our proof. It's just basically going to come down to this lemma. So we'll break it up into two cases, one where the order of G is finite, and one where the order of G is infinity. Consider the infinite case. Can anybody remind me, what does it mean to say that an element of a group has infinite order? Peter?
It means if you keep doing the group function over and over again with the same element, you'll receive, well, you'll be able to produce an infinite number of different elements in that group.
Yeah, it means you'll be able to keep getting different things every time, and in particular, it will never get you back to the identity element.
Generate, that's the word.
Which is logically equivalent to what you just said.
Yeah.
So that just means if the order of G is infinity, then G to the K is not equal to the identity for any positive integer K. That's kind of what that means by definition. Hence, phi of G to the K. Hence, for any positive integer, K, if we were to take phi of G to the K, well, or that. We want to be able to show that phi of G, if we take it to any power, we can't get the identity element in the second group, right? Well, phi of G to the K is by definition going to be equal to phi of G to the K, just using the lemma we just proved, that phi of G star phi of G star phi of G over and over is going to be equal to phi of G star G star G star G over and over. Well, we know phi of G to the K is not going to be equal to phi of the identity element in the first group. Should have E1 since we're talking about two different groups here. So basically, we know phi of G to the K is never going to be equal to phi of E1 because G to the K isn't equal to E1, and phi is on, and since phi is 1 to 1. Since G to the K is not equal to E1, phi of G to the K can't equal phi of E1, since phi, we're assuming, is 1 to 1 as part of being an isomorphism. Well, phi of E1, we know from property number 5, that has to be the identity element in the second group. And so this then tells us that phi of G to the K power can never be equal to the identity element in the second group. So if we're going to take phi of G star phi of G star phi of G over and over again, we're never going to get the identity element of the second group. I.e., phi of G to the K will never equal the identity in the second group. Hence, phi of G has infinite order as well. So in other words, if G has infinite order, then phi of G also has to have infinite order. And then, you know what? I'm going to let you do case 2 on your own. It's very it's similar to this case. You just need, at some point, you will get the identity element instead of we'll never get the identity element. But case 2 is the case where G has finite order, and it's done very similarly. Okay, that's going to do it for today. This big theorem might show up on the next homework assignment. It's not on the exam. Nothing on the exam requires isomorphism, homomorphism properties, but will likely show up on the homework for after fall break. So, in the meantime, I hope you all have a good rest of your day, and I will see you all on Monday. Monday, we're going to start talking about cosets. And get into what it means to take a quotient group.